is Hassan Alkhayuon, and we were here another interesting talk about zombie fires.
Yeah, thanks, Melinda, and thanks to the organizer for this wonderful opportunity and wonderful workshop so far. I enjoyed it quite a bit. So I guess, yeah, we heard a talk by Sebastian yesterday about zombie fires, and today I'm trying to kind of extend what kind of the model that Sebastian presented by including two effects. So first of all, seasonal variation in temperature, which Sebastian touched on yesterday, but I'm going to go a little bit in more details. And I'm also going to include a kind of a combustion term in this peat soil. So needless to say that this work is joint work with Sebastian, and I have to admit that the first time Sebastian told me he had a project about zombie fire, the picture that came to mind is this picture from Game of Thrones, which is based on the fictional work by called A Song of Ice and Fire. And for those of you who are not familiar with Game of Thrones, this is basically supposed to be a zombie dragon throwing icy fire, but yet the fire is still cold and hot such that it melts down a giant wall of ice. So it's kind of like very fascinating things. But actually, I wasn't too far off. So if you think of if you think of zombie fires, it's basically, as we learned yesterday, it's a kind of fire in peat soil, and it happens in kind of extraordinary cold places like this. This is probably from British Columbia in Canada, and you can see that the ice on the surface while the fire underneath. I have a video to show you what's going on there. So this is around February or March of 2 years ago. Yes, so the fire season hasn't started yet, and yet you see that the ground is still kind of cold and icy and kind of like there is snow covering the ground, but there is kind of fire underneath the surface. We also saw this picture from Sebastian's talk yesterday, which basically kind of represent the rate of warming, and then you can see that the globe is warming the fastest in the northern regions there, which happens to have kind of a large content of peatlands there. And there are some also experiments from the literature. I mentioned this paper. There's quite a bit of literature. I mentioned this paper by Rostikia et al., where they do some experiments where they have some peat in furnaces, and they heat it up to a certain temperature, which is way below the combustion temperature or the burning temperature of peat, and they leave it there for a while, and the peat start burning. So it's kind of like self-ignition in peat. And with these things in mind, so fast warming evidence, experimental evidence that peat could self-ignite. Now we kind of pose our research questions there. Is kind of zombie fire is basically rate-induced effect. And well, spoiler kind of from yesterday, Sebastian already made the case that it is, but I'm going to try to push it a little bit further today. So the rest of the talk, I'm going to present the model, which is a non-autonomous model of peat soil. It's try to make it as simple as possible, while at the same time including some kind of non-obvious effects. And then I will take you through how we modeled combustion very quickly, and I will give you kind of examples of rate-induced tipping to zombie fire in that model. And then I'll try to take you through how we explain these and how, particularly, how we try to find the critical rates or critical kind of thresholds for these transitions. First, through taking kind of like few transformations on our model just to convert it from a non-autonomous model, which we can do very little about, to an autonomous, fully autonomous model. And then I'll go back to these canards that we heard about yesterday. And then later on, I'll try to regularize the problem, so we reduce this kind of irregular rate-induced tipping problem into a kind of classical rate-induced tipping problem, where we have the critical rate is given by these connecting orbits between saddles, before I conclude at the end. Okay, so let's get started. So this model, some of you have seen it yesterday. So it's basically a very simple model. You have two variables. You have the soil temperature, this big T there, and then you have the carbon content of the soil, which is C there. And then if you look at the equation for the temperature there, so the first term is basically the soil temperature is trying to relax to the atmospheric temperature, which is there, TA of T in red. So this is kind of a time-dependent term. So this is will act as the forcing term in our model. And you have this mu parameter, which is the soil heat capacity. Lambda is the how fast this soil temperature relaxes to the atmospheric temperature. And then the next term in the T equation there is the reaction. Okay, so my reaction rate is a function of temperature. So this is H of T, and it's proportional to the carbon content of the soil. And there is also a conversion rate, which is A. That's a constant there. Now, you can think of this model for these for those who do kind of population modeling in the audience. This could be thought of as a kind of a resource consumer model. So you have the temperature consuming carbon, and you can think of this H of T as your functional response, basically. Okay, so whatever being consumed from the carbon equation over there is being converted into temperature in the first equation. And now the last term there, pi, which is basically a constant, that's a linear increase in soil carbon due to decomposition of organic matter over time. So I have two terms that I kind of put in color there. So the first one is the atmospheric temperature. And the atmospheric temperature, the way we model it very simply, yet we think it's kind of somewhat realistic than looking at the constant temperature there. So we have two components of the atmospheric temperature. Here's this. So you have a kind of an annual oscillation with a frequency of 1 year, and this delta AN is basically the amplitude of the annual oscillation. And you also have this term, which basically represents a heat anomaly at specific point in time, that's TH, and which has a maximum of delta H over there. T average is just the average annual temperature. Okay, so if you plot this function, you have some oscillation over time around TH, which is in this case is 0. You have kind of a certain increase in temperature, and we say that there is a heat wave if this kind of heat anomaly exceeded some critical level, which we call it T star there. Okay, so and the duration of the heat wave is the duration of time where you exceed this critical level. Okay, so this is about the forcing. Now we look at this reaction term over there. So the original, the first time this model has been mentioned is back in 2011 by Luke and Cox. They used this idea of the Q10 idea, which is basically you are asking yourself for each 10 degrees Celsius increase, how much does the reaction term increase? And by definition, this kind of give you an exponential process. So you can see this is kind of a straight line in the log scale, so it's exponential growth. But as Sebastian kind of made the case yesterday, this is kind of not realistic for higher temperature, because higher temperature you are basically killing off all of these microbes in the soil, which give you this respiration effect. So it's realistic to assume that at some point this kind of reaction rate would slow down because you don't have enough microbes in the soil. And this is basically what Sebastian presented yesterday, but we also wanted to add some combustion effects. So there are some kind of chemical reactions, multiple kind of complicated chemical reaction happens in peat soil on high temperatures. And we thought, okay, we're gonna represent them very kind of try to make it as simple as possible, yet we try to fit it to some realistic kind of experiments from the paper I mentioned earlier. So what we end up assuming is that there is another exponential growth that kind of take effect on higher temperature. So for temperature larger than 100 degrees Celsius, for example, the effect will be visible. And this effect also kind of slows down and kind of decays for higher temperature. And the reason being is that at some point the fire would generate lots of carbon dioxide and other gases that mask out oxygen from the kind of local fire environment and slow down the reaction. And then now these two kind of die-off temperatures, you could basically find them from the literature. So the first one is quite easy, is basically computing the temperature at which the microbes started to die. And then the second one, there are some realistic measurements for actual fires, which basically record like the maximum temperature for recorded surface peat fire is around 300 degrees. Okay, so that's where we set these die-off temperatures there. Okay, so now we have kind of a model there. We want to do some experiments. And in these experiments, I'm going to represent the temperature in the upper graphs and then the carbon in the lower graph there. The gray curve over there is the forcing term. And you see that my forcing term is kind of like oscillating, kind of seasonal oscillation. And then there is a kind of like a heat wave at specific time t naught or t equals 0. And then you see that the heat wave is basically quite small in comparison to the atmospheric temperature. So for kind of short enough heat wave, you would expect the soil temperature to rise a little bit. So that's why you jump a little bit over there. But over time, you relax back to the kind of the normal oscillation. And you see the carbon content almost never change. Now, for a slightly longer heat wave, so you see now my rate parameter, that's the multiplied by the time argument inside the sesh function. If it's smaller, meaning that the heat wave is slightly longer. So for a slightly longer heat wave, the temperature of the soil kind of undergoes this excitability effect that you also saw in the talk yesterday, and you kind of move to a hot state around like 70 degrees Celsius, and you stays there for more than a decade there. So this is kind of like a transient metastable hot state, during which the carbon kind of get depleted over time very, very slowly. Now, so the difference between this figure and this figure is a change of the rate of warming, which basically this is a rate-induced effect. Now, for the next experiment, I'm going to fix the rate. The rate is going to be exactly the same. I'm going to change the phase at which the heat wave hit. So if the heat wave hit, I don't know, in July or June, the second heat wave hits, let's say, in the fall, sometimes in October or September, for example. So if you have a heat wave in September, then you excite the system a little bit, you kick it to the hot state, which stays there for half a year or so, and then comes next summer, the kind of the zombie fire get ignited, and it lasts for a couple of years. Okay, so this is another metastable state in the system. You can actually use kind of these experiments to characterize a whole region in the parameter space. So here, for example, I fix my, I'm going to call it the phase parameter, TH to be 0.3 there. And I'm going to look at the parameter space of delta H, which is the maximum heat wave there. And I'm going to look at the rate parameter, which characterizes how long is the heat wave going to last. And you can actually distinguish three different regions in the parameter space. The first one, where the heat wave does not induce any transition in soil temperature. The second one, yellow, that kind of you have a heat wave to, a transition to a hot metastable state. And then the red one, you have a kind of a sequence of tipping from a cold state to hot state and then to a fire state. You can also do that. You can fix delta H and then look at the phase versus the rate, which is basically what the talk is going to be about, is kind of the interplay between the phase and the rate. And then you could also look at these different regions with different behavior. Now, the question we are kind of interested in, okay, these are kind of different regions in parameter space. What happens at the boundaries? And that's kind of the, the kind of questions we would like to answer. And before I kind of move on and explain what's going on, I have to, like, my system is a non-autonomous system with two time-dependent variables there. So I would like to kind of try to transform it into an autonomous system that I can work with. So, well, the figure there is supposed to be kind of a schematic figure. The colorful time series there represent two variables in the system, and then the gray time series basically represent the forcing terms in the system that I would like to incorporate autonomously in the system. So first of all, before we move on, you have seen that the different time scale separation between the temperature and the soil, and it's useful to rescale the system or non-dimensionalize it so that I know the time scale of the system. So I'm going to introduce these dimensionless variables, x, which is basically a rescale of the temperature, y is a rescale of carbon, and then tau, which is a rescale of the original time. I'm going to rescale my forcing term by also dividing by this reference temperature. I'm going to rescale my reaction rate by dividing by a reference reaction rate at the reference temperature. And I'm going to introduce a bunch of dimensionless parameters. You don't have to keep track of them, but just keep in mind that this parameter epsilon is a very small parameter, okay? So this will characterize the difference in time scale later on. And then the most important parameters that you should keep in mind is this dimensionless rate parameter rho, which is a rescale of the original rate parameter r, and this dimensionless phase parameter tau h, which is a rescale of the original phase parameter th. Okay, so I have a dimensionless system which has two variables, x and y. So this is y, this is x. And the reason I don't have labels there, because again, I wanted this figure to be kind of sort of schematic. And these gray kind of forcing terms are basically coming from the oscillation, the seasonal oscillation, and the asymptotically constant forcing term over there. So the first thing I'm going to try to do is to try to compactify time so that I include this asymptotically constant term within the autonomous system. And I'm going to do the compactification that Sebastian took you through yesterday. Unfortunately, I'm not confident enough to use the board, so I'm just going to do it on the slide there. So this is the system, just to keep in mind. And what I'm going to do, I'm going to introduce a new dependent variable that is S of tau, which is basically the tanh or the hyperbolic tan of rho over 2, nu over 2 into this rho into tau minus tau h. And the reason I use this tanh is because my asymptotically constant forcing term kind of decays exponentially, and more details about this choice you could find in the compactification paper that Sebastian wrote a couple of years ago. And now you should keep in mind that this variable S basically is asymptotically approaching plus 1 minus 1 as tau approaches plus minus infinity. And then this is the difference between these two kind of schematic figures. So this one is with respect to time, when time goes to minus infinity and plus infinity. And S, this one is kind of somewhat is a projection of the phase space now, because S is a dependent variable. So it's like kind of having a spring and then just contracting it into minus 1 plus 1 interval. And then this variable also solves an initial value problem, which is given by the derivative of S over tau, given by this right-hand side over there. And then you can see that we have to have the initial condition, which depends on the phase parameter. So what I had as the rate parameter is now kind of a parameter in the new differential equation, and the phase parameter is encoded in the initial condition for this initial value problem. You could also notice that there are two equilibria for this differential equation at S equals plus minus 1, which basically what we want, because S approaches plus minus 1 as time goes to plus and minus infinity. So I'm now going to take this equation there and rearrange for rho into tau minus tau h. So I have rho into tau minus tau h equals this term over there. And then I could take my forcing term and replace rho into tau minus tau h by the right-hand side of this equation. And then I could work out this using the expressions for sech and tanh inverse, the exponential expression of that. And I get a kind of a nice enough rational function there. I'm going to call it x sub h to the nu. And this is a function of the new dependent variable S. Is not a function of time anymore. Okay? So with that, I could rewrite my system. So I have the original two variables plus the new variable S, but now my asymptotically constant term is a function of the new dependent variable S. Now I still have this term which depends on time, and you can see it there. But this is easy because this is kind of just a periodic function. So what we could do, we could just introduce a phase variable, which is basically, I'm going to call it phi, and phi is basically tau mod 2 pi. And then what I'm going to do, I'm just going to write this term here as a cosine phi, and the derivative of phi with respect to tau is going to be 1, where phi of tau is between 0 and 2 pi. Now, the phase space of this system is 4-dimensional. So one projection that you could represent it is this kind of projection that we come up with. And let me take you through it because it's a bit involved. So because S goes to plus 1 and minus 1, as time goes to plus infinity and minus infinity, I'm going to represent it as two circles. So you have the small circle represent S equals minus 1. The large circle represent S equals 1. And as you go around the circle, so this is your your phase variable phi. And now if you kind of add the other variables, so for example, if you add temperature, then you could have two cylinders inside each other. So this is this represents kind of the soil's temperature there. And it's a bit difficult to see, but what happens is basically you start by oscillating around with the small cylinder in the path limit, right? So this is, you start oscillating over there. And then as time goes on, you go from the small cylinder to the large cylinder, from -1 to s equals 1. And when the temperature rises, so you go up along the cylinder, you keep rotating around the large cylinder, and then when carbon runs out, you kind of drop also by oscillating back. And then at the end, you kind of keep oscillating around the big cylinder. For carbon, it's the opposite. You start at a very high carbon, you oscillate around the small cylinder, and as time goes on, you start kind of igniting this hot state or fire state. So carbon get depleted, and then you converge to the large cylinder, and then you spiral down there. Oops. No, it's just a delay. Okay, so if the temperature is close to the reference temperature that I scaled with, so if x is of order 1, then the derivatives of x with respect to tau, s with respect to tau, and phi with respect to tau are of order 1, whereas the derivative of y with respect to tau is going to be of order epsilon, so it's kind of like very small. So one thing to do in this kind of case is like you look at the geometric singular perturbation, and then you could come up with kind of a reduction for the model. It's called the quasi-static approximation or the layer approximation, and that is you send epsilon to 0, and then you fix the carbon soil to a constant. So basically, y is now a new parameter in the system, and this is the equivalent of having infinite amount of fuel in the soil. So you have infinite amount of carbon content. Now, well, this is kind of not realistic, but it gives you a nice approximation of what happens when you ignite the fire. But once you ignite the fire cannot be put down, because it's basically you have infinite fuel, so the fire would go on forever. And with that, you eliminate the carbon kind of variable there, and what you have the soil temperature, and then now it's easier to see kind of you start oscillating around the small circle, and then you go up, and then you keep oscillating around the big circle on top, and then the temperature of the soil never kind of come down. Now you can see that as you rotate around the circle, if you take a section throughout the circle, then you will intersect this section every full period, every 2 pi. Yes? So what we will do, we will have this section there, and we will define a kind of a return map. And this return map is defined from this section there to the section itself. And basically what it does, if you take a point on this section, you just integrate forward in time with 1 period, and that is your second image. Okay? And then you keep doing that, and what used to be kind of an oscillatory solution of the differential equation is going to be reduced into kind of an orbit for this map. Okay, so we started with a model that has that is basically a non-autonomous model with 2 time forcing terms, and then we reduced it to an autonomous 2-dimensional compactified map over there. And now I guess I have all the ingredients to try to work out my problem and work out these boundaries of these parameter regions. But before that, I can't emphasize enough this point where that my phase parameter, which was explicit in the original equation, is now encoded inside this initial condition for the compactified variable that I introduced. And I will come back to that later because it's kind of quite important for the talk here. So now if we consider the layer problem, so that is the three-dimensional system that I have with the temperature x as a variable, and also the compactified variable s, and the phase phi. So as Sebastian kind of explained yesterday, so this problem has a kind of like invariant subspaces at s equals -1 and s equals 1. These are, I'm going to call them the future and the past limit systems. And that for the future and the past limit systems, the layer problem has a unique, has up to 3 stable limit cycles and 2 unstable limit cycles for each of these kind of invariant subspaces. Now, when you add the dynamics of S, basically whatever stable in the past, you add unstable direction, and it's a saddle. Sorry, whatever stable in the past, you add unstable direction, and it's a saddle, and whatever unstable in the past, you add this unstable direction, and it stays unstable. In the future, whatever stables stays stable because you add a stable direction in the future, but the unstable cycles in the future, because you add this stable direction, they become a saddle. Okay? Now, if you look at these invariant subspaces, and I'm going to look at the projection x versus y naught, and I can kind of put together all of these 5 limit cycles, and I will get 2 critical manifolds at s equals -1 and s equals 1. They are identical because my forcing terms kind of vanishes as you go forward and backward in time. So I tried to produce some of the 3D pictures that Sebastian presented for the other example yesterday. The result I got quite horrible, so I decided to have this 2D projection, and you will see why in a minute when I try to plot the figures there. Now, this layer problem basically gives you the dynamics between these kind of branches of stable. So this branch is a stable limit cycle. This branch is stable limit cycle. This one is stable limit cycle. I'm going to call this kind of the cold state. This is the hot state. This is the fire state. And these ones that are unstable. So basically, the layer problem would give you the direction in between these branches. So if you start here, for example, the unstable direction the unstable dynamics of this limit cycle would kick you either to the right-hand side if you are on the right-hand side of that, or to the left-hand side with the fast dynamics. The same happens for this, so you either get kicked to the fire or to the hot state. Now, if you look at the full system, you could do the slow approximation there, and you could have the actual dynamics on the slow manifold. I'm not going to take you through the mathematics of this, but you can think about it intuitively. For low temperature, yes, you can accumulate carbon because for low temperature, this term there in the carbon equation is quite small, and then this term is relatively large, so you can accumulate carbon very slowly, and then the carbon would rise. For higher temperature, this term is going to be larger, so for higher temperature in this manifold, this one, and this one, carbon is going to decay because this term is larger than the linear growth of carbon. So this is basically all you need to know. Now, looking at the original system will have a single stable limit cycle. So what Sebastian called the most boring system, the most boring nonlinear system you can come up with a single stable, globally stable equilibrium. If you force it periodically, you got a stable limit cycle or a stable periodic solution in this sense. And what I did in my simulations earlier, I started at this stable periodic solution, and I started applying this heat wave or heat anomaly at some point. And what the heat anomaly does is that it brings down the whole the whole kind of structure of critical manifold down. So it allows the solution to slip over this fold there, and then either jumps to the hot state, which is this kind of stable slow manifold, or the fire state, which is this stable slow manifold. So just to show you what would happen there. So this is the green kind of experiment where there is no fire. So you basically lower down the structure of the slow manifold for a while, and then you bring it up, and then you manage to catch the oscillation. So you start oscillating around the limit cycle. You probably deviate a little bit, but then you go back, and then you oscillate back with the slow dynamics. What happens with the yellow experiment where you tip to the hot state is basically you lower this structure of slow manifold, and then you slip over the fold, you go to this slow manifold, and then you keep going down until you hit this fold there. You jump back, and the slow dynamics will bring you up over time very, very, very slowly. Now, what happens in between these two cases? Okay, it's actually you have this very kind of difficult to get solution where basically you slip and you get caught on an unstable slow manifold for a while, and then you oscillate down for a while, but then because it's an unstable slow manifold, you either slip to the right-hand side or to the left-hand side, and in this case, it's called canard without head, so you slip to the left-hand side. Of course, you could get another solution very kind of close by, so you slip to the other side. And this is basically these families of solutions that give you, these are kind of it's not unique solution. So you could go up to here, up to here, up to here, and then for each case you get another canard, okay? So these are kind of infinitely many solutions in an exponentially small region in the parameter space, and you get this region that formulates your threshold behavior. Now, I also showed you this fire state where you have the red trajectory. So, by the way, the y-axis here is going very long, so I break it down. That's why you see this discontinuity. It's an artificial discontinuity there. And then, so the threshold behavior between the yellow solution and the red solution is also kind of like canards with heads, canards without head. That give you, that basically visit this another unstable slow manifold there. And then this one, the canard with head. And I think, Sebastian, you went over this notion of canards with heads, canards without heads very quickly. So I wanted to kind of show you basically why we call them canards there. So if I kind of flip my critical manifold counterclockwise and try to plot this canard with head on that. So I oscillate around the limit cycle, and then I jump, and then I jump this unstable slow manifold and get caught in the second one. So I oscillate around there for a while, and then I jump there. I oscillate around there for a while, and then I jump back. And once I am here, so the carbon will accumulate over time. So I will circle back the limit cycle over there. Well, you could add some legs there, and I don't know, some wings, maybe you add an eye or something, and then you get some sort of a canard. And canard without head is that basically, speaking of headless birds, So you basically, you don't do that. Instead, you either go all the way to the top or you jump back at some point. But in this case, you could go all the way to the top and then you get a maximal canard. I must say there must be some subtle things between birds without heads and tipping points. We should probably talk about this more a little bit, yeah. Okay. But so this is basically sort of like irregular rate-induced phase tipping, where the critical behavior or the critical rate will give you these kind of like special solutions that track some elusive quasi-threshold, as Sebastian put it yesterday. But actually, you can regularize this problem. So you could look at the layer problem. And we did look at the layer problem earlier, and we produced this autonomous return map. And then I'm going to look at the autonomous return map and try to say something about this kind of rate-induced tipping problem with respect to that map. So just to remind you of my map over there. And this map has up to 10 fixed points. 5 of them are saddle, 2 of them are repellers, 3 of them are attractors. You could see it there. It's basically so you look at the S variable and you know that there are invariant subspaces at S equals -1 and S equals 1. So for S equals -1, the path limit system, you have 3 saddles which represent they are stable within the invariant subspace, yes? And then you add the unstable direction in S. So this is the past cold state, the past hot state, the past fire state, and then in the future they are stable. So you have the future cold state, a future hot state, future fire state, and then the unstable solution or the unstable fixed points in the future, they are saddles because you add this stable direction flowing into the future. And now, since we have saddles in the past, saddles in the future, we would like to understand the kind of interaction of their stable and unstable manifolds. So first, I'm going to look at the cold state in the past, which is P1 minus, and the unstable cold state in the future, which is P2 plus. So the stable manifold of this, if you have a large rate parameter, it will limit backward in time to the unstable point P2 minus. So this is kind of a typical kind of codimension 0 behavior. The unstable manifold of this point will limit forward in time to the attractor in the future. Okay? This is, again, it's a typical kind of behavior. And I just remind you, these are manifolds of maps, which are basically not solutions of differential equations. These are kind of a set of orbits of maps, okay? So you could have an orbit that jumps on this manifold, and you have another orbit that jumps on this manifold. You can't flow along these manifolds. Now, if you change the rate, and I'm choosing the critical rate here, so you get a sort of a tangency of these two maps. Yes, thanks. I'm almost there. You get a tangency of these two maps. So these maps start intersecting, for example, here. But because they are invariant manifolds, if you iterate this point forward, you get another tangent intersection, another one, until you reach the future saddle. Back in the future, they are also invariant. So you iterate backward, and then you get an intersection. You reach the point P1 minus. And basically, what you have there is you have a heteroclinic connection between two saddles for this map. Now, if you perturb your, if you kind of decrease the rate parameter even further, you get this tangle behavior, which basically it's kind of like there is a very subtle message here. I'm trying to put it as clearly as I can. So if you are below the blue manifold. So basically, you keep the blue manifold is orientable manifold. So if you are below it, you would keep being below that manifold forever. So if you choose a point here, you iterate it, you get a point here, and then there, and then there, and then at the end you end up at the cold state. If you are above it, you keep being above this blue manifold forever, and then you end up at the hot state. And then as you iterate backward and backward, these intervals are going to kind of be smaller and smaller. And there's a kind of profound fact that if you take a neighborhood of the saddle, no matter how small, you will have two initial conditions. One of them will limit here, the other one will limit there. But I kind of made it clear that initial conditions in S is basically correspond to different phases. So what you see as an effect of initial condition in this map is none other than the phase tipping we have been kind of talking about all way long. You could, choose kind of a slightly higher, or sorry, slightly lower rate, and then you get another tangency. But this is kind of on the other side, where basically everything tips apart from this one kind of critical orbit that limits forward into the saddle and backward into the other saddle. And then if you do it further, you have this full tipping or total tipping in the system. You could do the same so this is only to tip from the cold to the hot state. You could do it the same for tipping from the cold state to the hot state to the fire state. And then you also have kind of these tangencies and transverse intersections of manifolds, which basically correspond to the unstable manifold of P1 and the stable manifold of P4 in this case. But just for the interest of time, I'm not going to do that. I'm just going to give you kind of like a full picture there. So by kind of parameter space there, the kind of the boundaries are basically given by these canard regions, which are basically quite kind of exponentially small, but they are still regions nonetheless. And if you use this heteroclinic connection idea that we use for a map, you could actually approximate, if you choose the layer correctly, you could actually approximate the kind of the first order approximation, at least, for where these thresholds should be in. With that, I'm just going to take you through my conclusion. I presented this non-autonomous model for peatland soil. I also give you examples of tipping to metastable hot and zombie fire states in the model. And then we did some transformations. We explored this critical behavior as kind of canard solutions. And then we regularized the problem, and then we reduced it to kind of connecting orbit problems similar to other regular R-tipping problems that we have seen throughout this week. Okay, thank you.
Thank you so much, Hassan. Maybe one short questions before we go to the more mathematical questions. Isn't precipitation, rainfall, snowfall relevant as well for zombie fires in that region?
I think so, yeah. Yeah, definitely. I mean, for realistic settings, yes. But this is just kind of like somewhat a toy model that we assume the respiration would dry out the peat and produce enough heat to induce combustion. And
could you integrate that as well? Like, or it would be
well, you could. I mean, I've seen some models where they have like multiple stages of peat fire, where the first stage is drying out, the second stage is respiration, and then you have even the combustion reaction there is kind of like combination of multiple different reactions, and that they have like an equation for each one. But very, very quickly, you get a very complicated model that you can't do much with. So.
Yeah. Thank you. Yes, thank you.
Thanks, Hassan, for the nice talk. I have a question about your model. So could you jump please to the beginning? Original. Yeah, maybe this one. Yeah, okay. I'm slightly worried about the second term, last term of the first equation. Because what it suggests is that increase in temperature is linear to carbon. But it's not linear.
It's not.
It's actually, the data shows that it's logarithmic. So why do you use it as linear?
Well, I mean, it's proportional to carbon, but it's not linear in.
I mean, dependence on carbon. So there is lots of evidence that the temperature, atmospheric temperature average or whatever, it depends on amount of carbon logarithmically, not linearly.
Do you have a reference?
It's not.
But that's soil temperature.
Yeah, it's a soil temperature. Why do we talk about global warming? Yeah, global warming means average temperature of a lower level of atmosphere, right? So I mean, it's not detrimental, but you know, logarithm can approximate to the linear function, of course, quite nicely. So maybe you should figure it out a little bit more carefully because it's not at all obvious that it should be linear. And
But
it's not, in that sense, it's
you are
not
talking about the atmospheric temperature, not the carbon, or are you talking about the carbon?
talking about the atmospheric temperature.
Okay, so the atmospheric temperature is this term over there, which is it's not linear. It's
No,
also
but T capital is
soil carbon.
so
Underground.
no, it's not like that, right? So your second equation says that carbon taken from the soil, both atmosphere, right? That's what you said. And then because of the increase of carbon in the atmosphere, temperature also increases, right? So there is a-
No, what I'm saying is that T is soil carbon, and if you ignore the reaction, then the soil carbon would relax to the atmospheric temperature with a rate lambda.
Hassan Sergey is right in the sense that this effect is not in the model.
Yeah.
So atmospheric temperature is imposed externally, but if you want to include all the feedbacks, it should actually increase proportionally to the amount of carbon that is being emitted into the atmosphere, and that effect is not.
The feedback from. Oh yeah, it's well, okay. We don't have it.
It's not coupled to C, it's just imposed.
Okay.
But if you want to include the feedback, your TA should be a function of C. So how much was emitted, or C initial minus C, so the amount that's been transferred to the atmosphere. So in a way, it's a sort of conservative model, because if you take this into account, the warming would be even faster.
Yeah.
But what he does, he just sort of runs this scenario that if you that is IPCC.
I understood what he does, right? But I'm just saying that it should be figured out a bit more carefully, because also there is another way to look at it, right? So if you slightly transform your system, you can show that in the left-hand side there will be derivative over time, a certain linear combination of temperature and carbon, and that derivative is proportionate to difference T minus TA, which means for the adiabatic slow increase, it's roughly conserved, which means temperature is directly proportionate to carbon, which is, I'm not sure, it's probably okay as an approximation, but we should be a bit more careful about it. So when we're presenting it.
I think if your point is that do we have any feedback from the carbon released from peats to the atmospheric temperature, that we don't have that in the model.
What I'm saying is that if you transform your system, right, multiply the second equation by A, add them together, right? So then the last terms will disappear. So what you will have. So what you have in the left-hand side, you will have d over dt mu t plus AC, right? Which means, and this is proportional to lambda times t minus ta. Means for adiabatically slow increase, that's roughly conserved value, which directly says that the increase in temperature, okay, in the peat soil is proportional to carbon. Is it really so? I'm not sure, but maybe something to check.
But you have
Yeah.
also the term of pi. You have pi also. When you multiply by A, you have to add pi.
Yes, that's a good point. Yes, that's a good point. But what once again, what is pi?
pi is
It's a linear increase in carbon over, like it's a very slow increase due to decomposition.
For what processes, what is it? What-
decomposition of organic matter.
This is how you get time.
So
Yeah.
for the sake of time, maybe,
Constant.
so there is one more question and then we have to continue with the reading.
Actually, really nice talk. I mean, somehow, because of something that Sebastian said yesterday, I had a similar concern, but I think it's different in the sense that I think a more fitting model would have an EPM on top. Because then, if you have an energy balance model, because you said the carbon in the peat soil is several times the one in the atmosphere.
Seven, but it's a bit more, but not twice as much.
So, but it's reasonable to expect that this will affect the evolution of temperature in a way that it
Only if you burn all the people at the same time.
So what we see in the model when we see this inversion, we actually see a decrease of the peat, which is substantial, close to zero. So in fact, this will have an effect on the temperature of the atmosphere if we drive it with an energy balance model. This will change the dynamics of everything, of course. But one other thing that I wanted to say is that even if we augment this with an energy balance model, which I think is very interesting actually, to see what happens. The interesting part of this talk is that you have a slow fast system with a with the dependence on the fast time. And there is a theory from Triasten from the 90s, sort of slow fast system with dependence on the fast time. And he has a very horrible statistical convergence of measures and whatever, because he didn't really know about attractors. But one of the things that we did with Rafa and Anna last year, it's in the JD, it's to actually explain this. It's not trivial, but to explain this in terms of not the slow manifold, but the slow family of attractors with dependence on the fast time, which has the very positive fact of being very mild irregularity and also not necessarily periodic, but any time dependent. So this would allow to explain very rigorously and very easily also your excursion on the slow manifolds. Then now just this slow family of attractors with fast dependence on the fast time. So I think this is
Yeah,
interesting.
it's interesting to have a
Yeah.
more chat about this.
So I show you the arch then.
Let's give Ulrike the
Yeah,
floor now. Thanks.
let's take Hassan again.